things like this. Uh-oh. I do have a problem. Wait a second. Let's do this again. Ah, yes. Sorry. Ah, it looks better, isn't it?
Yep, we can see it.
Very good. So, so as you know, the title of this lecture is the Star Height Problem. My name is Jean-Éric Pan. I'm working in Paris. And this will be a random walk through combinatorics, some algebra, a little bit of logic, and some topology as well. But I will try to explain everything. So please, if something is unclear, immediately interrupt me. We are not that many in the audience, so you can just open your microphone and tell me when you don't follow. So to start, I would like to fix some notation. So I use notation for words, letters, alphabet, which is on the screen. And so the alphabet is A, as A for alphabet. In this lecture, I will use mostly a two-letter alphabet with A, B. And so the words, you can see some example, A, B, A, B, A, B, A. And there is a special word, as you know, the empty word, which I denote by 1, because it's the identity for the product, the computational product. So a language is a set of words, as you know. So you have this. So this is the first example. This is another one, an infinite one. And the set of all words is denoted by A star. This is also the free monoid A. Is that clear to everybody? So what are the usual operation on language that I will be using? So you have the so-called Boolean operations, union, intersection, complement, which I denote by L with a C as an exponent. The product, concatenation product, is a component-wise product. So you take a word in the first language, a word in the second language, you concatenate them same and you take all of them. And the famous star operation, which you can define in two different ways. Either as just this infinite union, the empty word union L, you know, the product of L by itself and so on, or in a slightly more algebraic way, it's just a submonoid of A star generated by L. So what are the regular expressions? You probably also know what they are. You start with the empty set or with the expression reduced to the empty word. You could also start from the letters, so in my case, A and B. And then you are allowed to use union, product, and star as operation. So here are three examples: empty star, and this one, where I use union, product, and star. And this regular expression represents regular languages. But an important fact is that if you have a given regular language, it can be represented by many regular expressions, and actually it can be represented by infinitely many regular expressions. So just take this example. You see that A is the alphabet, so this is AD. So this is a regular expression for this language. This is another one. This is the third one, or you see that I have this nested stars. Well, the second one doesn't have much. This one is a little bit more sophisticated, but it still represents the language A star. So every word can be written in this form.
And Dr. Pin, from the regular expressions perspective, what's the difference between the empty set and the set that only contains one?
There is a difference because the empty set represents the empty set. And so for instance, yes, let me go back to this. For instance, this empty set star would be equal to the set reduced to the empty set. So that's the difference. Okay, so that's the regular expressions. And let me say a little bit about the restricted star height problem. So as you remember, the title of my lecture is the star height problem, but I want first talk about the restricted star height problem, which was also a very famous problem, but this one has been solved. So what it is, it works in this way. Let's have a look at this example over there. Yeah, this one. So you see, this is a regular expression. You see some union, product, and star, and you see some labels. And the red labels, which I call level 1, the blue label, which I call level 2, and the green label, which is level 3. And so this expression is as a restricted star height 3 because it has the maximum nested depth of stars in this expression is 3. So I don't want to make this definition formal, but I hope to see what it means on this example. Is that clear also? Yeah? Yeah. Thank you. So now, going back to languages, the restricted star height of a regular language, it is the minimal star height of a regular expression representing this language. So you look at all possible ways to represent the regular language, and you try to find an expression with the smallest restricted star height. Okay? And so this problem was asked back to 1963, or a long time ago, more than 60 years ago, no, almost 60 years ago, which was, given a regular language, can you compute its restricted star height? And to start with, are there any language of star height 0, 1, 2, 3, n? And this problem has been completely solved. So let me just briefly review this. So first of all, it was proved just 3 years after the problem was raised that there exists a language of restricted star height n for each n. Okay, good. And next, it was proved by Hashiguchi first that one can decide whether a language is as a star height, but it should be restricted star height each time. Okay, so restricted star height 1 is decidable, meaning that I can decide whether a language has restricted star height 1. And later on, Hashiguchi proved that restricted star height is decidable. So for each n, you can decide whether a language has a star height 8.
Dr. Pin, in the statement that for each n there exists a language of restricted star height n, is that given any arbitrary alphabet, or is that where you're allowed to choose the alphabet beforehand?
That's a very good question. Actually, the example given, the original example given by Dejean and Suttenberger involved language on an n-letter alphabet, but you can easily transform it into a two-letter alphabet. So okay, it could be more precise. There exists a language on a two-letter alphabet of restricted star height n. So
I guess what I'm wondering is, it seems to me like it would be a trivial proof because you would just take n symbols and then put a star on each one. And if they're all distinct symbols and you put them in a row, then that language could only be expressed with that many symbols, right? Or am I misunderstanding?
Yeah, well. Remember that the star height is
it's the depth.
the nested depth.
Right. Okay.
So it will not be it will be a language of star height 1.
Right. Okay.
Right.
Yeah.
So anyways, this was the first proof by Ashikusu was really almost unreadable, basically. But fortunately, Kirsten gave a much simplified proof, still very technical, not technical, but very difficult, but it could be understood. And moreover, the complexity is now known to be in double exponential space for this algorithm. And this problem has got many consequences on things like max plus and tropical summerings, regular construction. I don't want to go into this thing, but just to say that this is a still alive topic of result. But now, let me come back to my original and topic of this lecture, which is star height. So for star height, I'm not using regular expression, but I'm using something called extended regular expression, which are just the same, except that now I'm using complementation on top of union product and star. So, and since you have this well-known formula, you can freely add intersection if you wish. So here you have an example of an extended regular expression. I'm using union, intersection, complement over there, and star. So this is an example. So now we can do exactly the same thing. The star height of an extended regular expression is obtained at exactly the same definition. This is the maximum nested depth of stars. So for instance, in this expression, you know, you have here the first level 1 and the second level 2. The complement doesn't count for the level, so this extended regular expression has star height 2. Very good. So, just in the same way, what is the star height of language? There is no restriction anymore. The definition is this is the minimal star height of an extended regular expression representing this language. Okay, so now we are going to do exercises, practical exercises, and I need your help. So we start with the star height 0, and these languages are called star-free languages for some obvious reason. You want to, if you have star height 0, you have no star at all. And the question is, I give you there is a long series of languages, and we will try to see whether one can say whether these languages are star-free or not. So let's start with the first one. What do you think about A star? Is it star-free or not?
Okay, clearly has a star, right? It
has a star, but remember, it is a minimum of all expression. So, does anybody see it? There is actually a trick. The trick is, I give you the trick. The trick is, don't forget you are allowed to use complement. So what is the complement of this language, for instance?
It's complement of empty set.
Exactly. So let me write it this way. Okay, so you see on this expression, there is no star at all. So, which means that this language is star-free. Okay. Next one. What about this one? Again, it looks like there is a star. Anyone has an idea in the audience?
I think you need the star for that one, because you would have to subtract B star in order to get A star, and either way you're writing a star.
Well, what is the complement of this language?
It's everything that contains at least one B, right?
Exactly. So let me observe this. So what you just say is that this is everything that contains a B, at least, is this, right? But this is this. Okay, so therefore, A star is this. Okay, that's the trick. So this language again is star-free. So what about the next one? This one is easier actually.
So it's basically B followed by everything, and everything can be empty set complement.
Well, actually, basically, the first thing you can do is each time you have this capital A star, just use the first equality, this one. You can just replace every A star by empty complement. So that's, you make things simple. So you can write this as A, this, and the next one also. I can write it in this way, right? So this makes that, so therefore, again, these two languages are star-free. Okay, let's move to the next one. This one is much more tricky, actually. But the trick again is to look at the complement. If you have ideas, please tell me, otherwise I will help you because that's not so easy. Okay, I will give you the solution, but even the solution needs to explanation. So what I will do, as usual, I will try to compute the complement of this language. I claim it is a complement of what? It is a complement of this things okay? So what does this mean? What does this represent? So look at a word in this language, in this complement. Okay, so this a word which is not in this language, which is not in this language. Well, it could be the empty word, certainly. It could be the empty word. But if it's not the empty word, the first letter is not allowed to be a B. So if the first letter is not a B, it's an A. No, sorry. It's an A. What is the next letter? Well, because of this condition, I don't want to have two consecutive A's in my expression. So the next letter has to be a B. What is the next letter of such a word? Well, now I don't allow to have two consecutive B's. Well, therefore, the next letter is an A. Sorry, next letter. The next letter is an A. The next letter is a B. Blah, blah, blah. And so you see, I have the word of this form: A, B, A, B, A, B, and so on. Well, but what is the last letter? Well, now I'm not allowed to have A as the last letter. So therefore, the last letter has to be a B. And you recognize now your language. Okay, so now you can elaborate on this. And of course, now when you have this, just replace A star by the complement of the empty set. And so the conclusion is this language is star-free. Also, it doesn't look. So what about this one? A star, which is apparently simpler than the other one.
So it can't have a B and it can't have an odd length, right?
Yeah. So actually, you're right. Actually, we will see, because it's not easy. So that's not so easy to prove that this language is not star-free.
Yeah, because all length is very hard to encode, right?
Yeah, but okay. Now I have a bunch of languages, and if you just want to guess which one is star-free, which one is not star-free, just use this example here just to show you that this is not especially simple. So this one, sorry, which one? This one is star-free. The next one, that is this one, is not star-free. This one, the next one, is star-free. And the last two ones, both are star-free. And actually, especially this one is amazing, because you have this pattern AA and BB inside under a star. So you're saying, well, it looks like this one, which is not star. So at this point, I guess you just get confused. And the conclusion is, well, we need an algorithm. Well, actually, question, is there an algorithm to decide whether a language is star-free or not? There is one, and I will show you this algorithm. And so for doing this, I need to go to algebra. Well, as you will see, this is not a very sophisticated algebra. This is computation of syntactic probability. So let's start with my favorite example, AB star. So here you have the minimal automaton recognizing this language. I guess even if you don't ever seen any automaton, that's very easy to see. You start with you start at the state 1, you read A, you read B, and you have to write at state 1. So you can loop as much as you want, and you recognize this thing. So what I want to do is convert this automaton into a monoid, and the way I do this, I consider A and B as partial maps from 1 to itself. So A maps 1 onto 2. This arrow, so I write this 1 onto 2. From 2, there is no image, so I put a 0 just to say it's not undefined if you prefer. So I write it this way. And for B, it goes from 2 to 1. 2 to 1. And in 1, it is undefined. Okay. So now I want to compose from this table, and I want to do this for all words. So if I start with, first of all, let me start with the empty word. the empty word is considered as the identity. It has the identity on the state. So if you start from 1, you stay in 1. If you start from 2, you stay in 2. So let me just add 1 here, just to say that it acts as the identity. Next, I'm looking at words of length 1, which I already did. The words of length 1 are A and B. And then I proceed to compute the word of length 2 in alphabetic order. So let me compute the words AA, AD, BA, BB. So what about AA? If I use AA, I start from 1. As you can see, A, and then there is no way to go. So it's actually, I arrive into 0. If I start from 2, reading AA, I also arrive in 0, because this column will all be 0, so I will not fit it. And so this, so I can consider this element as a 0, because it is acting just as a 0. So I try to do this. Yes. So the next one is AD. AD is interesting. What does AD? So you start from 1 and you read AD. If you do it, I read A, then B, and I write in 1. So I write 1 AD is 1. If I start from state 2 and I read AD where I can't, go to 0. I think that's a new element. So let me continue. Let's do it for BA. BA. If I start from 1, I can't read any base, so this will be 0. But if I start from 2, B and then A, I arrive in 2, so this is 2 and 2. Very good. Now, if I do BB, what happens if I do BB? Well, if I start from 1, I can't read B. If I start from 2, I can read B once, but I cannot read BB. So actually what I got is that BB is actually exactly the same as AA. So you will end up with the 0, 0, 0 map. So let me keep this as a relation in my monologue that BB is equal to AA is equal to. Well, now I'm not finished because I just did the words of length 2, but I need to go to words of length 3. So let's go. If I start, so what are the words of length 3? Normally there are the word starting with AA, so there is AAA and AAB. Then there is ABA, ABB, BAA, BAB, BBA, BBB. The point is that I don't really need to compute the words which start with AA or that start with BB, because I already know that BB is 0. If you use this map, if you are in state 0, which is a non-existing state, you stay there. So actually, I don't need to compute this. I don't need to compute this. I don't need to compute this. And I don't need to compute this either, because there is a B, nor this. So that's a good news. I just have to compute ABA and BAB. Okay. So what is ADA? To compute ADA, you start from 1 and you read the A you arrive in 2, right? From 1 you go to 2. And if you start from 2, you can read anything, so it's 0. But now you recognize that ADA is just the same as A. Okay, you see this is exactly the same thing as this, 2, 0, 0. So what I do is I'm adding this relation, ADA is A. And now I can do the same with BAB. BAB, DAB, if I start from 1, I arrive in 0. If I start from 2, whoa, stay. Okay. If I start from 2, E, A, and B arrive in 1. So again, it's 1, 0, and again, this is just the same thing as B. So let me write this. B, A, is B. So now I have my monoid. What I want to compute is this. M is 1, A, B, A, B, B, A, 0. And it is defined by this relation. ABA is A, BAB is B, AA equals BB equals 0. So now, if I want to multiply 2 elements to know the product, it's sufficient to use this relation. So for instance, imagine I want to compute AB times BA. I write it as A, BB, A. This is 0 and this will be 0. Okay. So do you see how I obtained this this monoid from this automaton?
Yeah.
Very good. So this was an example. Let me do this other example, which is much simpler because there is only one letter. So here we have the identity as empty word gives the identity. And what happens if I compute A squared? Well, obviously, A squared is again the identity. If you start from 1, you arrive to 1, and if you start from 2, you arrive to 2. So in this case, you have a much simpler monoid, which has 2 elements with the relation equals, yeah? And so this is just the group of order 2. Right? Now, what did I compute all of this? Because as this is useful to characterize Star Height languages, but I still need another definition, which is the definition of an aperiodic monoid. So a monoid is aperiodic. A finite monoid is aperiodic whenever, if you start with any element x and you compute the successive powers of this element, well, it's stationary. So in some sense, so you have some n such that x to the n is equal to x to the n plus 1. Okay. So in order to, I would like to illustrate this definition on my two examples. So you recognize the monoid I just computed before. And I want to check whether this monoid is eperiodic or not. So for this, I compute the powers of the successive element. So the first one is 1 squared is 1, okay, obviously. A squared is 0, so a cube is also 0. Same thing for b squared equal b cube equals 0. And ab, that's more interesting, ab square is ab. But here we know by this relation that this is A, so therefore this is A. So this element is idempotent, it is equal to its own square, and in the same way, this is BA. So you see, we have found for each element X, if you compute this as a successive power, then it stabilizes like this, xn equal xn plus 1. So this monoid is eperiodic. Let's consider now, let's go back to this one. Well, if you compute A, start with A, then you have A squared equal 1, then A cube is A. A4 is 1, A5 is A. And you can see it, so it alternates between A and 1, but you never have x to the n equal x to the n plus 1. So it's not a period. It's not a period. And now, here comes the big result, which is due to a second theory, which tell you that a regular language is star-free if and only if its syntactic monoid is eperiodic. This is a kind of really amazing result if you consider it was proved back to 1965, where automata theory was not that advanced at the time. And I just don't know how he managed to find this connection between this very combinatorial property of star-freeness and this very algebraic property of syntactic monoid. But it worked. And the proof is difficult. There are essentially two proofs, but one is by induction on the structural properties of the monoids, and you need some semigroup theory. And the other one makes use of the Cronwald's theorem or the Risch decomposition of monoid as well. So both proofs are difficult. Just to be complete, the complexity has been analyzed, and it turns out that if you start with a finite deterministic automaton, as we did, you want to decide whether it accepts the star language, and this is p-space complete.
Is it p-space complete and you find the language, like you come up with a witness, or is it p-space complete regardless of whether or not your proof includes actually determining what the language is?
So you want to decide. I give you a finite automaton, but just like the one I gave you before.
Mm-hmm.
That's the input. And the output is yes or no to the star language.
Okay, without necessarily actually writing down like the
exactly.
smallest.
No,
okay.
Yeah. Actually, if I remember correctly, the length of the shortest star-free expression is a tower of exponential length. It's very long. For instance, for the example I gave you, it would be impossible to write it maybe on one page.
Is there a connection between this result and finite cyclic groups? Because it, I don't know, morally feels like maybe there's a connection, but
yes, yeah. Actually, there is one connection. Yes, there is a deep connection actually. So if you need to go a little bit inside semi-group theory. So I mentioned the role of idempotence. Okay, and you can prove that if you have a finite monoid, if you have an idempotent, any idempotent in a finite monoid is contained in a maximal group. And being aperiodic means that these maximal groups are all trivial. So actually another name for aperiodic monoid is group free. If you look at the literature, you'll find group free. And so, yes, it is really connected to this. Of course, if you have a syntax monoid, this is a group, it's certainly not stuff, except if this is a trivial group. The answer is definitely yes. So I wanted to make a short visit to logic, just to show you that this is also related to other things. And I don't want to go too much into formalism, but just want to give you an intuitive definition of this, of the logic I want to use. So here you consider a word, you, okay? And you want to say something like, this U contains an A. So more precisely, there is a position I in your word, which carries an A, which I indicated by this arrow there. So you have some A inside the word. But in terms of logics, you would write, there exists I, which means there exists a position, and AI, so A is a predicate applied to the variable I, which means that in position I, there is an A. And so now if you take all words satisfying this formula, it's a language, it's a set of words which contains an A. So can you describe this language? So any idea?
like with an automaton or a regular expression?
A regular expression.
So I think it would be A star, A star.
Exactly. It will be this. Yep. Now, almost the same. Now I'm saying there are two positions, I before J. I carries an A, and the J carries a, oh, J carries a B. So in terms of logic, I would write it in this way. There exists a position I, there exists a position J, I is smaller than J, and AI and J. So in the same way, it would define, well, the language, basically, A star, A star, B, A star, right? And I had some two exercises here for you. Find a formula for we do it in the reverse way. Find a formula defining this language, A star.
So we just write A subscript 0, right? If we're 0 indexing, and that would be, you don't even need a quantifier.
Yeah, but the problem is you don't have access to 0 officially in my logic. So what the trick instead is to say there exists a position I, which will be the first position. So how can I say this? I can say that
Smaller than everything?
exactly. That there exists an I such that for j, I is smaller than, or let me write it this way. Normally I should write smaller than or equal, but okay, let me allow this. And AI, right? And so it should be in red.
So examples 1 and 2 would be like the F or eventually formula in LTL, and example 3 would be like the X or next in LTL.
Okay. Okay. You will see. I mentioned the LTL later on, but you're right. You're perfectly right. So if you want to do the next one, A star, what you could do is say there are two positions I and J. And you want to say that, so I is smaller than J. And you want to have A, you want to have this, of course. AI in J, but you want to also say that there is nothing between. So
for everything, okay.
yeah, exactly. For every K,
That is greater than J, it's greater than I.
yeah, so you don't have this. There is nothing between, okay? There is no K which is strictly between I and J. Okay, anyway, you see, this is the idea. And now there is this beautiful result by Robert McNaughton, which tell you that first order formula captures Starfree languages. So what does this sentence mean? It means that if you start with Starfree language, you can find a first order formula. So first order, I guess you know what it is. It means you have variables which represent just, yeah, sorry, you have quantifiers just about on variables. And so if you start with Starfree languages, you can find a formula, first order formula, which represents the language. And conversely, if you have a first order formula, it necessarily represents the Starfree language. So you may wonder what happens if I have a regular language now, just like A star. Actually, this is interesting because this theorem was proved before. It was proved by Bucci in the 60s, that regular languages are captured by monadic second order formula. So monadic second order means that you can quantify, you are allowed to quantify on sets of variables.
So Dr. Pin, is that why we say Bucci automaton? Because every LTL formula can be expressed using monadic second order predicates, and each of those could be captured by a regular expression or something like that?
Yeah, so every regular language can be computed expressed by a monadic second order expression, formula. And if you have a monadic second order formula, it defines a regular language.
Okay.
But I want to show you what you need to quantify on set. Just for instance, this language is not Starfree, but I can still use this formula. There exists capital X, so this is a set now of position, a set of position, such that, and I want to say that the first position, which I call bin, is in X. The last position is not in X. And And for all x in x is equivalent to the successor, so x plus 1 is not in x. So I'm cheating here because I'm using min, max, and plus, which are not defined, but I can express them by a first order formula. Let's use this as an exercise. And so if you look at this now, assume you have, if you compute the position from 1, you will have 1 is in x. Okay, sorry, where is this? You should not read this too fast. Yeah, okay, so you have, sorry. The elements which are in x and those which are not in x. So you know that 1 is in the first position, is in x, but because you have this code, so 2 is not in x, but 3 is in x, 4 is in x, is not in x, and and so on, and you end up with the maximum, which will be the length of the word, is not in it. Okay, so it implies that this is of the word has an even length. So that's the truth. Now I don't want to detail this, but anyway. So I had this note just for you because you mentioned linear temporal logic. It turns out that this is a result of 10. That linear temporal logic also captures stuff in language, which in some sense really shows that this is a very important subclass of regular languages. It corresponds to many natural things. So one other consequence is that A star is the language of star at 1, because it's not star free, and obviously it is a star at 1. And actually, we know a little bit more. So for instance, it can be shown that if the syntactic monoid of a language is a commutative monoid, then the language has star at most 1, just like in this case. And furthermore, and that's much more difficult to prove, that if you have a group, if the syntactic monoid is a group of small order, less than 12, which is very small, then the language has star at most 1. Okay, it's not 2. But the next question is, well, okay, but is it possible to obtain an algebraic characterization of the language of star smaller than 1? That's, if you have, we have seen Schuttenberger theorem is very nice. We have an algebraic characterization for the star-free languages. So as the hope was that, is it possible to have this? And for this, I will need to go beyond languages, and I would to talk about varieties. So let me just mention this, and after that, maybe I'll. Okay. So what is a variety of languages? It's a class of regular languages which are closed under three things. First of all, Boolean operations. The union, intersection, and complement. They are closed under so-called residuals. Well, this is this operation. this one, if you know about the neural automata, that's exactly what it is. So if you probably know that if the language is regular, its residue is also regular. And the third one is a bit more technical. If you have phi from A star to another alphabet, is a monoid morphism. Then the L variety of languages, regular languages, let's say call it V. Lay L in V implies the inverse image of L in V. Okay, so they are closed on the inverse closure on the inverses of morphisms. That's what we say. Those are the abstract. So you want example. So first example, regular language. Second example, star-free languages. Third example, regular languages whose syntactic monoid is a finite group, no, necessarily finite. And there are myriad, plenty of examples. So, I'm not sure if you have time to.
Groups are an example as well, right?
Sorry?
Are groups an example?
Well, groups, I'm talking about variety of languages, so just at the level of languages. So they are regular languages with syntactic monoid as a group form a variety of languages. This is a third example. But you can have many other examples like this.
Gotcha, yeah.
Originally, I wanted to make a short break. We'd like to have a short break if you want me to keep going.
Anybody in the audience have an opinion about this? I think whatever you prefer, Dr. Penn. I'm happy to keep on going. But if you'd like a break, we can do a
No.
okay.
No, I can keep going.
Okay.
Yes. So let me. I will just maybe add. So let me mention this. So there is a theorem by Allenberg proved that varieties of languages, regular languages, can be characterized by some equations of the corresponding syntactic monoid. So this is a very loose statement. I could make, or I would try to make it precise, but I'm not sure to be able to do this completely. But let me just give you the idea that, for instance, you have star-free languages. They correspond to aperiodic monoids, which correspond to, which are defined by this kind of equation. For all x, there exists an answer that x plus n equal xn plus 1, right? That's what we are. The problem is that this form of equation is not that nice because it involves these quantifiers, and especially this n. So one can avoid this by using topology, but I'm not sure I want to do this right now. Maybe I can try. So we want to rewrite this equation in some way. And for this, we need some topology. So let me start by defining a topology on a finite monoid. So you have the discrete topology, which is defined this way. Okay, well, we skip this question. So this, it turns out that you can verify that the product is uniformly continuous, so this discrete metric. And now I want to do something not on the finite monoid, but on A star. The idea is that intuitive ID two words are close in this metric, this new metric, if one needs a large monoid to separate them. And instead of monoid, I could use automaton, if you are more familiar with this. So what does it mean? It means that suppose, for instance, I have the words A to the n. Well, these two words. Okay. So I'm looking for an automaton which accepts one, but rejects the other one. So as you can see, so what would be in your opinion, what would be the smallest automaton or monoid which separates them?
think A star would work.
A star. Sorry.
No, double A star, like
Yeah,
double
exactly.
A parenthesis star.
Yeah, exactly. So what you observe is that this has even length, and this has odd length. So if you take just this automaton, okay, then 1A100 would be 1, but 1A101 would be 2. Okay, so which means in terms of algebraically, it means that you have a map phi from A star to M. You say a monoid separates two words. If you have a morphism such that phi of u is different from phi of u. This is exactly means that phi separates the word u, right? So that's my definition of separating. So in this example, well, I can separate them by this monoid cyclic group, even, not even. Okay? And now, if I want to make it a metric, I do the following. So I keep this ID, but I denote it by R of UV. This is the size of the smallest possible monoid, which separates the word u and v. One can show that it is always possible to find such a monoid, just like you can take a finite automaton separating two words. And now the metric is 2 to the minus R of UV. This is just to adjust things in such a way that if you need a large monoid, to separate them, I told you they are close, but the distance will be very small. And it turns out that this is really a metric, and furthermore, you have a special property called ultrametric, which means that instead of the triangular inequality, you have this max instead. Okay. This metric on words is, first of all, it's very difficult to compute. If you want to, it's very difficult to get an intuition on it. I'm sorry for that, but makes sense. On the other hand, it is well behaved. I let you, as an exercise, to verify that the translations are continuous in the following sense. You have the distance between x, y, and z are words. You have these two properties here. So they are continuous, and moreover, the product is a uniformly continuous map. The proof is very simple. If you want to compute the distance between x1, x2, and y1, y2, you use this strong inequality. You insert y1, x2 in the middle, here and there. So you use this equality. Now, you observe that using 1, you can replace this by this, and that's it. So it is well behaved. So the product is uniformly continuous. So now I'm ready to define the profinite monoid. So what it is? We know that A star D is a metric, is a monoid. And also a metric space. Okay. So if you remember your first course on topology and metric spaces, you know that every metric space has unique, essentially unique up to isomorphism, a unique completion. You remember? A metric space is complete if every Cauchy sequence is converging, and there is a completion. So let's call it, let A star hat be the completion of A star. Okay. So the profinite monoid is just this, well, just it's a completion of A star D. As I told you, it's rather difficult to explain what it is. It's not just like when you construct the real numbers, it says it's completion of Q, but every one of you knows what a real number is. The problem with A star hat is that I have no such description. The only thing
the limit points are going to be infinite words, right? I mean words, but like infinite sequences of letters.
Not really. That's
okay.
That's the first problem. It's not an infinite sequence of letters. They are just the limits, the abstract limit of Cauchy sequences. But I will give you actually one example of a one convergent sequence, which convert to some element in a minute. But it's counterintuitive. So it has nothing to do with infinite words. It's really different. That's the first point. The second point is that this space is, A star is countable, but this space A star hat is not countable. Okay. And actually, this is an open problem to have a nice description of this space. But still, we can use it. Okay, so I told you I want to describe your Cauchy sequence, but one thing which would be useful to know is that essentially, so I don't want to be, essentially, the profinite, what I call a profinite word, an element of this A star hat, is known through its projections onto finite monoids. So the idea is that if you have phi if you have a monoid morphism from A star to a finite monoid, then it extends in a unique way into a continuous monoid P hat from A star hat to M. The M is discrete, okay? So this is D, then discrete. So if you have this, basically two elements Oh, okay, no, sorry. If you have two elements, U and V, in A star hat, then U equal V, if and only if, for all morphisms from A star to N, phi hat of U is equal to phi hat of V. Because this is exactly what I mean by essentially a profinite known is known through its projections. If you know the image on every finite monoid for every morphism, if you know these values, phi of U, you are done. This value phi hat of U. But let me go to this the unique concrete example I will be able to give you, which is this one. I'm considering a finite monoid, a finite semigroup X, and now I compute the powers of this monoid, of this element, X squared, X cubed, and so on. So since it is finite, there is some P such that you have this, so P is a period, and after that, so you loop around this element, sorry, around the circle, xi plus p is it's equal to e to the I. And it's not very difficult to show, and there is a short proof here, if you want to read it, that on this circle, that is, there is some powers, which usually denoted by x to the omega, which has the property that x omega is an idempotent. So there is a power of x, which is an idempotent in a finite semigroup, always. Okay. Moreover, this circle, the element on the circle, I remember I mentioned that each time you have an idempotent, you have a maximal group. In this case, it is very easy. The maximal group is just the C-cube group over here. That's exactly what it is. So it's okay. So here is a short proof. I don't know if you want to read it, but all I need to know is that if I take an element x, some power will be an idempotent. I denote this by x to the omega. Okay, but there is something very, very, very remarkable. Suppose that I have now a monoid of size n. Okay. Then I claim that for all x in n, x to the power n factorial will be an idempotent. Why? Why? Because you know that some powers will be, I don't know if some powers will be in the circle, over there, and the circle is a group. So if you are in a group, what I'm using here is that if G is a group, the finite group, x to the power G is the identity of the group. You know this. Okay, now, but if you have n factorial and n is larger than n, sorry, n is, so you certainly are, this power is a multiple of the size of the group. Certainly. So we just prove this for me. That's very interesting because it means that there is an element, you know, you have this remarkable formula, and this implies that limit You have this in every finite monoid. But actually, this is a constant. Okay. Ah, well, very nice. But actually, this shows that, well, I don't give the detail, but basically, we can show that x to the n factorial is actually a Cauchy sequence. And since it is a Cauchy sequence, it defines an element in A star hat. So this very formula can be used to define an element of A star hat, which is idempotent.
But if we didn't have the factorial, it would not be a well-defined limit, right?
Absolutely.
Okay.
Yep.
Yeah, it's kind of counterintuitive.
Yep. Absolutely. So this element x omega is very nice. And well, that's has slightly expensive. But anyway, let me keep going. Where I am. Yeah. Yeah. So I have this. And now the aperiodic condition, remember, can now be written as x to the omega is equal to x to the omega times x, or if you prefer, x omega plus 1. And actually, if you want to be precise, x omega plus 1 should be defined as the limit of another Cauchy sequence, which is this one. But that's perfectly good. So now, that's very interesting because now we really have equations. So the condition means that the language we start from if and only if it's syntactic monoid satisfies the profinite equation x omega is 1 for x omega. Which means what? It means that if you consider the map from A star to the syntactic monoid of the language, as we did, it extends and you take then and x is in A star hat now, then phi hat of x to the omega is equal to phi hat of x to the omega. That's formally written. But then you don't want to go into this abstract setting. Really what you mean is that each time you go to the finite monoid, you go back to you look for the idempotent and you want to verify that the next element in the loop is x omega plus 1. So it's just this. But it's really a profinite equation. So it's a formal equality between two elements of A star hat. And coming back to Heisenberg's theorem, that's a spirit, it tells you that each time you have a variety. Remember that? Where is it? If you have a variety of irregular languages, it can be characterized by a set of profinite equations. That's exactly. Actually, that's Heidelberg and Reiterman. There are two parts. Okay. So, how is this useful for our problem? Yeah, so I have a more formal definition. If you wish, let me review this. So if you start with a finite monoid, you have a morphism, you extend it to A star hat by continuity. And now if you have two words of a profinite monoid on variables on X, then M satisfies the profinite equation U equals V if and only for every monoid morphism from X star to M, you have this T hat of V equals 0. And a periodic monoid of X. Commutative monoid would be defined, that's very easy, by the equation X1 equals YX, not very surprisingly. Groups are more interesting. What would be the equations for languages with syntactic monoid with a finite group? This is the answer. It will be this. X to the omega equals 1. Why? Remember, X to the omega is the idempotent generated by X. So if you have a monoid in which every element, the unique idempotent is the identity, a finite monoid in which the unique idempotent is the identity, will be a group. So you see, this is very, very nice equation. You may consider that maybe you can construct every profinite word using this omega operator, perhaps. No hope. If you just have the omega operator, you still have a countable number of elements. Okay? Even if you consider something like this, some expression, you know, it's y to the, well, all these terms, there will be only countable many of them. And I told you, A star hat is not countable. Well, that's right. Anyway, so back to Heidelberg-Reiterman, in a more precise version. The class of regular languages is the variety of languages, even monoids. The syntactic monoids satisfy a set of profinite equations. Be careful. This is a set. This set can be infinite, basically. So in the case of star-free languages, we were very lucky. We had just one single equation, and more it was simple one. But this theorem doesn't say anything. It could be, the set could possibly be infinite. And moreover, it doesn't say at all which equations, which set of equations. This is an existence theorem. We tell you there is, the term varieties come from this. It is defined by equations, so it's just like a variety in mathematical sense, you know? But we don't do this. So what is it useful for the star height problem? So it boils down to this question. We know that star-free languages form a variety of languages. So what about the languages that start, say, smaller than 1? Big disaster. Well, maybe not. Actually, it was shown that if the languages that start at most 1 form a variety of languages, then all regular languages that start at most 1. So which would mean that there is no language of start 2.
Is that just because you take like the empty language and then you do product with your arbitrary language of higher star height, and then it has to be within your variety and you've arrived at a contradiction?
No.
Or is it a
sorry. the reason for this result is that actually you will see what is missing to be a variety of languages. But that's depending on whether you are optimistic about the language of Star Height 1 or not, it could be considered as very positive result or very negative one. I hope understanding this. So, what is the problem? So we don't know whether, basically we don't know whether the language of Star Height smaller than 1 form a variety of languages. However, we know that the languages of Star Height at most n, even n, are closed under Boolean operations, the first point. They are closed under residuals, the second point. And they are closed under inverses of, not under morphism, but under inverses of length-preserving morphism. So what is a length-preserving morphism? It's just a morphism that maps a letter to another letter. Remember, these morphisms are between A star and B star. So if you send letter to letter, you preserve the length, of course. Okay, so it means that the length of phi of u will be the same thing as the length of. If you just consider this kind of morphism, then they are closed on the inverse of this one. So, but there is some hope. It turns out that Howard Straubing, in picture, managed to prove an extension of Heisenberg-White-Herman theorem. So now you consider a class of regular languages which are closed under Boolean operations and residuals. If they are closed under inverses of morphism, then they are defined by some set of profinite equations. This is just Heisenberg's item. If you are closed under inverses of length multiplying morphism, slight variation, they are also defined by some set of profinite equations, but here you require that all the variables have to be interpreted as words of the same length. I will give you an example to explain what it means. And the last case of interest for us, which is exactly the case where the class is closed under length-preserving morphism, then it can be defined by some set of profinite equations in which all variables are interpreted as letters. So, in order to illustrate the second case, I would like to go a little bit far from this lecture in talking about circuits, Boolean circuits. You don't need to know anything. Maybe you have heard of AC0 as just as a term. This is a class of Boolean circuits. I don't want to. It has a nice logical characterization as well. I don't want to go into that. But the interesting point is that I'm looking at the regular languages in this class. And these languages are closed under Boolean operation, residuals, in inverse of length multiplying morphism. And now, here comes the beautiful theorem by Barrington, Straubing, and Terrien, looking back in 1990. The regular languages in this class satisfy or are defined by some kind of profinite equation. You see this. This equation involves this omega operator I had before, so it's not that complicated. The difference is that now you want to interpret x and y as words of equal length. So if you go back to my example before, you would just replace, you remember the syntactic boundary of A star, you would have to replace x by some word and y by some other word, but these two words should be of the same length. So we have this kind of result, tell you that, well, you can characterize some classes. So let me be back to the star height problem. As I told you, the languages of star height n are closed on the almost varieties, are closed on the length inverses of length preserving morphism. So therefore, by the Schrodinger's theorem, they have a characterization by profinite equations where now variables are interpreted as legends. Okay, very nice. So if you are, so now there are two questions. So do you think if you think there is a language of star height 2, so it would suffice to find just a single equation satisfied by all languages of star height less than 1 to prove the existence of a language of star height. You don't even need to have a full characterization. If you just find a single equation, that's fine. You will take a language which does not satisfy this equation. That's it. But now comes the bad news. The bad news are 3 of them. The first one is that, as I told you before, this profinite equation are not new. I have no ideas what they are. Worse, it's quite possible that all regular languages have star height less than 1. And nobody was able to find any language of star height 2. So it's still an open problem to find a language of star height 2. So if you remember my first results and directions that I told you, it's quite, if the languages of star height less than 1 form a variety, full variety of languages, and every language has star height less than 1. It's quite possible. Nobody can, well, anyway, nobody was able to find a counterexample. So now you have a dichotomy. Some people think that every language has star height at most 1, and some other people think that, well, come on, there should be languages with star height 2. So what are the latents? If you want to practice, so here is a possible candidate. So you see this relatively long expression. It's apparently of star height 3, but well, I want to make it a candidate for star height 2. If you want to understand what it means, because the regular expression is a bit complex. It is, if you look at this automaton over there, it's just the set of words U, such that if you start from the initial state 0, you arrive to the final state 0, okay? But there is another condition, is that when you look the path that goes back to 0, it should use this red H, this one, an even number of times. Okay. So that's I think this is the smallest candidate that was not proved to be a star height 1. So if you want to practice, more generally, as you said, that group languages are a good candidate for star height. If you want to have a complicated language, take a complicated group, whatever it means, so at least of size at least 12, and take any monomorphism from A star to G, and take the inverse image of 1 into this morphism. You should find a rather complicated language. So this is in the direction of finding language of star height. On the other hand, if you think that every language has type 1, you may consider looking at things like this. You take F1 and F2, two finite languages. Okay? Well, and then you look at F1 star intersection F2 star. Okay? So since this is it can be rewritten as R star, because it's a monad, it's as this form. And if you compute some example, you will find that R can be really complicated to compute. So it tells you that basically we don't know much. Right? Look at this. I even don't use complement. And we have seen that the power of complement in this problem. But the complexity of this is such that we may just miss some powerful tools to obtain expressions of low star. So just in this direction, this will be my last comment. You can try just to look at this intermediate star height problem when you ignore complement, but you just allow union and intersection, the two complement in the definition of the star height. And even this one is unknown. So we don't know whether there are languages of arbitrary intermediate star height, whether it's decided. Okay, this is unfortunately a very still wide open problem. Also, we have seen we tried to push in various directions involving algebra, topology, even logic. There were some tries, I didn't mention them, but in that direction. But the problem, unfortunately, or fortunately, still open. Okay, thank you, and please ask questions if you. Well, there are plenty of discussion. Maybe we should do this.
Thank you very much, Dr. Pin. That was fantastic. I'll let other people ask questions first if they have any. Yeah, I guess, could you elaborate a little bit on the connection to complexity theory? I mean, you mentioned this earlier when you brought up, I think it's AC0 or something, that which I vaguely remember from when I took complexity theory a year ago, but not very well. But maybe there's some connection there where this problem is more difficult than it seems because it's somehow related to some difficult question about different classes in complexity theory, something like that.
Yeah, okay. Circuits, yeah. So, yeah, there are, there are various classes of complexity, and especially on circuits. And if you change, you see, AC0 is basically circuits using gates and or and not, which are polynomial size and constant depth, okay, and unbounded family. If you slightly change this definition to allow modulo 2 gates, or modulo 3 gates, or modulo 6 gates, you end up with new classes, and again the same questions arise. Can you separate them? I mean, especially there is actually, if you want to know everything about this kind of question, look at Howard Strawding's book, on circuit complexity and I don't remember the title, but it contains all of this. What I want to say is that in order to separate these complexity classes, you may try to separate them by some languages. So yes, there is this language majority and so on. Okay, but it turns out for AC0, this is very special because you can use regular languages to separate them. Okay, and that's the spirit of this theorem, was to use regular languages to separate AC0 from other classes. And the problem is that this theorem is okay, if I remember. It makes use of a deep result on complexity inside this proof. Also, it's a result on regular languages. We don't know of a direct proof of this proof without using this separation result, deep result separation result. And that's amazing. I mean, that's a nice result, but we don't have a simple proof. Well, not even a simple proof. We don't have an algebraic proof, purely algebraic. And there are plenty of classes. I told you, for instance, for the modulo 2, with the mod 2 gates, there are some results. For mod 3 gates, there are some results. But for mod 6 gates, I think this is still open whether it's the same. It's more powerful than mod 3 gates, for instance. So there are the progress has been extremely slow, are still very slow, extremely slow, both on the complexity size, because there is not so much progress in 20 years on this side, and on the regular side also. That's right. I mean, House solving has published a few partial results on this direction, but it's not that easy. But in general, yeah.
I'm sorry, I was just going to ask if you could comment on the magic number 12, because you
have
this theorem about 12.
No, 12 is just that I think once you get 12, which group do you have? Well, I don't remember which group we have, but there is the first, we still have solvable groups, but.
Okay, but you arrive at some interesting group and that's when things change.
Yeah.
Okay.
That's the first case we could not solve, but you know, this is so tiny. This is really impressive that the fact that we cannot even decide whether a language of star height 2 just means it. Come on. Is that possible, really? Well, that's like, you know, on complexities are the same. You know, we don't know whether P is space or something. So.
Cheng and Daniel or Kai, if any of you have questions, you should hop in. No, okay. Well, I have one that's kind of off the wall. Since we're talking about the completion of a metric space and we arrive in this kind of exotic, interesting looking space, I have to ask, do you think there's any connection to p-adic numbers, which would be the other, you know, interesting example of a completion of a metric space that I think a lot of people are aware of?
Yes, there is a strong connection with that. Okay, let me explain to you. I can explain this in 2 minutes. Just change my definition by considering morphisms not onto a finite monoid, but onto a finite P group, right? So you want to take two words, you want to separate them by a finite PD. You can prove this can always be done. Okay, now you take a one-letter alphabet. A star. Okay, so you define the same metric, but with p group instead of monoid. And what you get when you take the completion, you get p-adic numbers. If you go to a larger alphabet, you get to something called the pro-p group. It's always good. It's a compact group, where, by the way, star hat is also a compact number. So it's really related to that. And languages recognized by T group are extremely interesting. But actually, I could give a full lecture on them. Actually, I did. If you look, I think there is one which should be even on the internet. I was invited at some to give a lecture, and you can find it on the internet somewhere. Anyway, so yes, definitely yes, yes, yes.
Fantastic. Well, thank you very much for your time, Dr. Pin. This is absolutely fabulous. If people want to contact you, if you know, if Daniel has some breakthrough on the problem tonight and wants to get feedback, can they email you? What's the best way to contact you?
Thank you very much. Yes, it would be appreciated.
Okay, fantastic. And I'll post this recording online. I know that, for instance, Brennan had a meeting halfway through and had to leave. So some people want to watch after the fact. And yeah, we really appreciate your time. This is stupendous.
Could you send me the link? Also,
yes, will do.
Yep. Okay.
Yep.
Thanks.
All right. Thank you, Dr. Pin. Bye.
Bye.